Hello and welcome once again to the lecture series on transistor. We have started our discussion on transistor biasing, and in previous lecture we have discussed about the fixed bias technique. Here we'll be taking another very popular biasing technique which is known as self bias. Transistor biasing using the voltage divider circuit or potential divider bias is also popularly known as self bias. You can see the circuit here. In this case, it is one of the most widely used biasing technique because it provides very good stabilization. And here you can see that a voltage divider network using R1 and R2 is formed to make the base emitter junction forward bias. So because of this R1 and R2, we are calling it voltage divider bias. And here you see RE, the emitter resistor we are using, and this is a very important resistor. Later on, we will be seeing that it is very important to achieve good stabilization. So as I have mentioned, because of this R1 and R2, this resistor network, which is basically a voltage divider network, due to this self-bias technique is also known as voltage divider bias or potential divider bias. Now, let us analyze the input section. But before starting the analysis, we should have two important assumptions. So first assumption says that I1 is much greater than IB. Hence, we consider that the same current is flowing through the resistor R1 and R2. So we can say that I1 is flowing through both R1 and R2. So this is the first assumption. Second assumption says that IC is much greater than IB. Hence, instead of IE is equal to IC plus IB, we are considering IE is same as IC. So these two are the initial assumptions. On the basis of this, the entire analysis will be done. Now if we have a look here, that I1 is flowing through both R1 and R2. So we can say that I1 is VCC divided by R1 plus R2. So this is the current, this is the voltage flowing through the entire R1 and R2 resistors. So we can say that voltage divided by total resistance. So that is giving us the current I1. Now the V2, if we consider as the drop across R2, then we can say that V2 is equal to I1 into R2. So that is giving us VCC into R2 divided by R1 plus R2. So this is equation number 2. And here you can see that this voltage divider network, it is providing the voltage drop V2, which is basically providing the required biasing to the base emitter circuit. Now here, if we apply KVL in this particular loop, so we can consider this as the input loop. So in this input loop, if we apply KVL, then we can write V2 that is equal to VBE plus IE into RE. But we have considered IE is equal to IC. So we can write V2 that is equal to VBE plus IC into RE. So let us call it equation number 3. And if we further simplify this one, rearranging the equation 3, we can say that IC is equal to V2 minus VBE divided by RE. So this is the expression for the collector current IC. So call it equation number 4. Now we see that IC is independent of beta. So two parameters, earlier lecture we have seen that these two parameters beta and VBE, that basically influence IC. To make IC independent of beta and VBE, we are applying different kind of biasing circuit. So in this biasing circuit, straight away we can see IC is not directly dependent on beta, but we have slight dependence on VBE. But in practice, V2 is such that it is much greater than VBE. So as a result of that, IC is also getting independent of VBE as well, or it is very less dependent on VBE. Now let us have the output section. So this is our output loop. Now in this output loop, if we apply KVL, and this is the drop VCE. So we have three drops: drop across RC, drop across RE, and drop across the uh, collector to emitter. So you can write, by applying KVL, we can write VCC, that is equal to ICRC plus VCE plus IERE. But IE we have already considered, it is same as IC, so we can write VCC equal to VCE plus IC. If we take common, then we can write it as IC into RC plus RE. So from here, input and output relation we can draw as VCE equal to VCC minus IC into RC plus RE. So this is the output equation for the self bias technique. Now, how the stabilization is achieved here? So once again, if we consider from the input section, we find that V2, that is equal to VBE plus IC into RE. Now, suppose IC is increasing due to the increasing temperature. Now, if IC is increasing due to the increase in temperature, that in turn will increase the drop across RE. So, this network here, drop across RE will increase. Now, if drop across RE increases, that in turn will have effect on VBE, and that will eventually bring down the IB. So, if IC increases, then IB will become lesser. So, as a result of that, we know IC is equal to beta IB. Now, if IC increases, IB will decrease. Now, if IB decreases, that will further bring IC down. So, this resistor RE is taking the corrective measures, or we are using this RE for corrective measures. So, as a result of that, IC will never get out of control, and hence we are getting a better stability in self-bias method. Now, if we look into the stability factor of self-bias technique, then the stability factor expression is given as 1 plus beta into R naught plus RE divided by R naught plus RE plus beta RE. Now, how we are getting this expression, that I'll be discussing in next video. For the time being, we are considering this result, and here if we divide the numerator and denominator with respect to RE, then we can write 1 plus beta into 1 plus R naught by RE divided by 1 plus beta plus R naught by RE. Now, if we can choose R naught by RE in such a way that it is much less than 1. Now what is R naught? R naught is nothing but it is R1 parallel R2. So equivalent resistor of R1 R2 in parallel, that is what we are writing as R naught. So if we can make this is smaller and RE larger, then we can get a very small value of R naught by RE, which may be much less than 1 also. So as a result of that, we can ignore this term R naught by RE. So ignoring this term, we get 1 plus beta in the numerator as well as 1 plus beta in the denominator. So we can even achieve S equal to 1, which is the ideal value of S. However, in practice, getting 1 is difficult, though theoretically you can get. But in practice, getting it quite difficult. But we can keep S much less than 10 or in the range of 10. So that kind of stability can be achieved. And because of its stability, self-bias technique is universally accepted technique for transistor biasing. So we end our discussion here. Thank you very much for listening.